Hi everyone, thank you so much for joining our webinar today. My name is Anya. I'm a part of K-Mine business development team. And before we get started, please follow our LinkedIn page. This is the best place where you can follow our newest releases, updates, news, and upcoming webinars. So what are we doing today? We are diving into ways to support successful shift from open pit to underground mining. We'll explore how to evaluate key technical considerations, select the most suitable mining approach, and plan a smooth transition strategy, all with a focus on operational and economic efficiency. But before we get started, for those of you who are new here, I'd like to give you a quick intro to K-Mine. We were founded in 1994 in Ukraine, and over the years we've grown our presence throughout Europe, the United States, and Canada. Our team brings together a great mix of developers, mining engineers, geologists, and many of whom are qualified under NI 43-101 and JORC standards. We work with a wide range of clients, from small exploration teams to large mining companies, and we always deliver reliable, cost-effective solution that is tailored to each project's needs. So let me just tell you what we do. We build software designed specifically for the mining industry, so I would say from late exploration to the end of the production. And our platform includes flexible models that work both for open pit and underground mining. And what makes us unique is how adaptable the system is. You can start small with just like one module and over time expand to the full suite, whatever fits your needs. Our tools help manage geological data, create optimized mining plans for both short and long-term projects. And with the optional integration for IoT and dispatch systems, you get a real-time monitoring to keep operations running smoothly. But at K-Mine, our software is shaped by real industry experience. It's built to solve the challenges that we've come across in our consulting work. As I mentioned earlier, our team includes qualified persons who create reports that meet NI 43, SK 1300, and JORC standards. These reports are tailored to project stages like pre-feasibility, feasibility study, mineral resource estimation, and preliminary economic assessment. And we have a deep expertise in a wide range of hard commodities with a strong focus on critical minerals. So if you're interested in how we can support your project, feel free to leave a comment below or just reach out to us through the contact form on our website. So let's look at our agenda today. First, we'll look at how to determine the right transition depth from open pit to underground. Then we'll dive into the key geomechanical factors that impact that decision. Then we'll go over how to choose the right underground mining system for your deposit, and we'll also talk about phase transition strategies to help make the shift smoother and safer. Finally, we'll wrap up with a look at how to keep the whole process economically efficient. The shift from open pit to underground mining is a big strategic decision. It's based on a mix of geotechnical, economical, and technical factors. Usually the transition happens when going deeper with open pit mining stops making sense. One common approach is to compare the final pit outline. So it's often calculated using methods like Lurch-Grossman with an underground scenario beneath it. If the pit walls are close to their strength limits and you need a solid crown pillar to separate the two operations, pushing the pit deeper often is just not practical. The most well-designed pits already have steep and stable walls, so there is little room to go much deeper without risking safety or adding major costs. Besides wall stability, several factors affect the transition depth. These include the ore-to-waste ratio, equipment productivity, and the cost of operating equipment deeper underground. So the transition depth is set when the combined NPV of two-phase plan, which is open pit followed by underground mining, is higher. It must exceed the NPV of continuing open pit mining to the deposit's full depth. We use iterative economic and mathematical models to evaluate different pit and underground mining setups, choosing the one with the highest combined NPV. Studies suggest that this mixed approach can boost a project's overall NPV by about 2% compared to just open mining. In practice, the transition zone's lower boundary is the ultimate open pit depth calculated without considering underground operations. The upper boundary is the minimal practical depth for starting underground mining, like the depth of the weather zone or the required crown pillar thickness. Within this zone, the transition point depends on the factors like ore properties and infrastructure availability. For example, the crown pillar under the pit floor needs to be thick enough to handle increased stress, which limits the amount of underground ore you can access. If the pit is too deep, the pillar must be even thicker, which can hurt the project economic viability. The optimal transition depth varies based on the deposit type, ore value, and the host rock's geomechanical properties. Small gold open pit mines often shift to underground mining at 200 or 400 meters, while large porphyry copper mines can remain economical even at 700 or 1,000 meters. The decision is very case-specific, factoring in reserve structure, metal price, forecast, ventilation, dewatering, and other factors. For example, one large mine temporarily steepened pit slopes and reinforced walls to extend the pit's life by 2-3 years, bridging the gap until underground mining was ready. In other cases, companies mined depleted pit remnants for years while waiting for underground operations to start. The transition from open pit to underground mining hinges on balancing economic benefits with engineering limits. The optimal depth is reached when the cost of deepening the pit by another meter matches or exceeds the cost of underground extraction for the same ore volume. So you can start planning it from 5 to 15 years before the pit reaches its limit. If you identify the transition point earlier, you can ensure things like proper infrastructure, stable slopes, and maximum reserve recovery. And ultimately, choosing the right transition depth keeps the mine running smoothly and maximizes the deposit value throughout its life cycle. One of the biggest factors shaping the choice of underground mining method once the open pit phase is complete is geomechanical conditions. Key factors include rock strength, fracturing, in situ stress, pit slope stability, and host rock properties. Rock quality is evaluated using systems like RMR, Q, or GSI, or strength criteria such as Hogg-Brown criterion, which helps create limit state diagrams for various scenarios. For example, the Hogg-Brown criterion uses rock strength and structural data to define ultimate rock pressure, aiding in accessing pit slope stability and predicting roof collapse. In strong uniform rocks, like intrusive types with UCS above 150 to 200 MPa, pit slopes can be steeper, around 45-60 degrees, allowing deeper pits. In weaker, fracture rocks with UCS below 50 MPa, slopes must be gentler, under 40%, restricting pit depth. Most economically designed pits have slopes angles already maximized within geomechanical limits, so deepening further risks instability or requires impractical pit expansion. At this stage, choosing an underground mining method suited to the rock strength becomes critical. Different underground mining systems place different demands on the strength of the rock mass. In strong rocks with a low fracturing and high UCS, like over 100 MPa, large, stable chambers work well, making a room and pillar or large volume blast methods such as sublevel stopping ideal. For moderately strong or mixed rock masses prone to collapse, the backfill methods like cut and fill or controlled caving such as sublevel caving are better, where the hanging wall collapses after ore extraction. For example, sublevel caving is used in Sweden and Ukraine's iron ore deposits because the magnetite ore is so strong with UCS around 200 MPa. The surrounding weaker host rock naturally fills the void after blasting. Block caving was once thought suitable only for weaker rocks with UCS from 6 to 60 MPa that could naturally break under their own weight. However, advancements over the past 20 years, like hydraulic fracturing or preconditioning blasting, have expanded block caving to strong rocks. For example, in projects like Keria East or North Parks in Australia, DMLZ in Indonesia, El Teniente in Chile, and Palabora in South Africa, all of these projects have successfully implemented block caving in rock masses with UCS values of 140, 170 MPa, even up to around 300 MPa at Palabora. This is comparable, by the way, to the strength of granite, which was previously considered unsuitable without forced fragmentation. This shows how geomechanical analysis and engineering rock breakage are broadening method applications. As depth increases, the in situ stress field becomes an important factor. Hydrostatic stress combined with strong brittle rocks leads to rock burst risk and prevents the use of large excavation chambers. So stope sizes shrink or caving methods are used to relieve stress. For example, at greater depths over 800 or 1,000 meters, pillar-based methods like room and pillar are rarely feasible due to pillar crushing, and the preference is given to either backfilling the mine-out space to support pressure or caving to allow controlled stress release. By the way, when shifting from open pit to underground mining, it's essential to consider stress redistribution. Decades of surface mining can create tension zones, and fracturing near pit walls and underground work beneath these areas can trigger collapses and water inflow through the relaxed zones. Geomechanical experts have recorded that the presence of a mine-out open pit above the underground mine alters rock mass behavior. For example, at Palabora, reactivation of movement along fracture zones on the northern slope occurred after underground ore extraction began beneath the pit. So what happened is the loosened mass began to subside into the caving zone. These risks guide method selection. If an unsupported pit lies above, methods like gradual caving that reduce seismicity are preferred over the large blasts. At the same time, surface stability can directly dictate the mining methods. For example, experts from SRK have noted that preserving pit and surface infrastructure often drives the choice of underground system. So let's talk about what's the deal with accessing deeper reserves after the open pit phase. Once open pit operations are completed, you can access deeper reserves through a haulage decline, like inclined shaft or decline, and vertical shaft, or combination of both. Your choice will impact the project's economics and safety. Generally, vertical shaft works best for deep deposits and high production volume, while declines are better for shallow deposits with moderate output. A rule of thumb from South African mining suggests that if you're going deeper than 300, 500 meters and need to move thousands of tons of ore daily, shaft makes sense. Shafts are great for quickly hoisting large amounts of ore to the surface, think of hundreds of tons per hour. But for depths under 300 meters or smaller scale operations, a decline is often a smarter choice, and it's quicker to set up and costs less upfront. Calculations show that as the required production increases, the optimal cutoff depth for switching to shaft access moves higher. For example, with a daily production rate of 5,000 tons, the decision in favor of a shaft is made around 500 meters depth, whereas at 1,000 tons per day or less, a decline can still be effective even at 800 meters depth. Also, different countries have historically developed different approaches. For example, in South Africa, most deep mines use shafts for depths up to 3,000 meters, where in Australia there are examples of mines using spiral declines with a truck haulage at the depth of 1,000 or 1,200 meters. So choosing the access method is a tailored decision that also takes into account cultural factors, if you will, like local expertise in shaft sinking or the cost of electricity for hoisting. Also, geometry and the size of the deposit are critical factors in selecting the mining system. A wide, gently dipping ore body, like a thick zone with inclined layers, is often best mined using a decline with multiple access points. On the other hand, a narrow and steeply dipping vein is more practically accessed with a vertical shaft, especially to reach deeper levels quickly. Tabular or sheet-like deposits usually favor development of a decline along the strike of the ore body, whereas vertically oriented, pillar-like ore bodies typically require a shaft to provide central access to all levels. Combined schemes are also very common in practice. For example, the John D. Gold Mine in Australia, after exhausting the pit, initially developed a decline to mine the nearby underground sections, and as the depth increased, they installed an auxiliary raise shaft for hoisting ore. And this approach reduced initial capital expenditures and spread it over time. The required production rate and haulage also play a big role in choosing the access method. For large-scale underground mining, like tens of thousands of tons of ore daily in block caving at major copper mines, the truck haulage through a decline can create bottlenecks. So think about hundreds of truck trips causing congestion, needing strong ventilation, and driving up costs. In these cases, shaft hoisting and conveyors are often necessary. For example, Palabora mine. The block caving there produces 30 to 33,000 tons daily using a vertical shaft with a skip hoisting, handling about 20 million tons yearly. Similarly, at Chuquicamata's plant block caving, underground crushers and conveyors are key to managing up to 140,000 tons of ore per day. For lower production rates, like 500 to 1,000 tons daily, using trucks via decline makes sense, offering flexibility and lower upfront cost. However, as depth increases, the cost per ton kilometer rises faster with declines than with shaft hoisting. So safety and ventilation are also critical for high traffic declines with exhaust gases and equipment heat demanding powerful fans and air shafts. That's why the modern deep declines often use electric locomotives or conveyors, or they're limited to the depth about 700 to 800 meters. The access methods needs to work hand in hand with the chosen mining methods to create a seamless system. For example, block caving often calls for multiple shafts, one or two for ventilation, one for hoisting ore via skip or conveyor, and one extra for emergency exits. Building these shafts take a lot of time, so mines often start small with a ventilation haulage decline to prep initial workings, while deeper reserves wait for the main shafts to be ready. For room and pillar mining with selective stoping common in narrow gold veins, a single spiral decline and a small ventilation raise are usually enough. Production is modest, so flexible access to reach isolated ore zones quickly is key. Take sub-level caving at large iron mines like Kiruna in Sweden or North Mine in Canada as an example. They are using hybrid systems, spiral declines for equipment access, and vertical shafts for ore hoisting. At Curinavara, ore is hoisted from 1,365 meters level via vertical skips, but for operational needs, there is a truck ramp from surface to approximately 600 meters with further access through shaft level infrastructure. So the decision is not necessarily decline or shaft. In practice, a combination is often implemented to leverage the advantages of both approaches. Also, where you place the portal also matters. If the open pit is still operational, the decline can be driven directly from the pit wall or floor, eliminating the need for a separate surface portal and reducing development length. At the Argyle Diamond Mine, for example, the portal edit was set at the pit's lowest level for quick access below the floor without complex surface works, though it needed extra slope reinforcement to prevent collapses during pit operations. For a vertical shaft, the collar side is peaked outside the pit's influence zone, usually beyond the crest at the safe distance to avoid risks from wall instability. The crown pillar beneath the pit is designed to keep underground work from destabilizing pit slopes until surface mining wraps up. Choosing the right access system is all about safety and practicality. If you're using a vertical shaft, it needs a reinforced lining and backup hoisting system, usually a second cage to support the skip system. For decline, you'll need safe turnouts, clear evacuation routes, and alarm systems, and in longer declines that are several kilometers or more, emergency plans must include bypass raises or alternate escape routes. International standards say that if a decline is more than a few kilometers long, a second exit is required. This has shaped access planning in many deep mining projects, and that's why engineers often go with a hybrid setup. Take Suiba gold mine in Brazil, for example. They use a main shaft for hoisting ore and moving people, but also build a spiral decline to connect levels, move equipment, and provide emergency exit. It's a bigger investment upfront, but it boosts safety and gives you more flexibility in operations. Moving from open pit to underground mining isn't a single step. It's a long overlapping process. At large scale mine, planning for the shift usually starts around 10 years before open pit operations end. So there are several key stages along the way. First, you need to explore deeper ore zones. Then you need to decide on the best transition depth and mining method. Then you need to design and build underground infrastructure. Then you have to run both the pit and underground mine at the same time and slowly winding down surface mining while ramping up underground production. One common mistake is underestimating how long this process takes. It can lead to production gaps when the pit is done, but the underground mine isn't quite ready. So in this case, a phased transition helps to avoid that. A big concern is pit stability. As underground mining begins, the bottom of the pit becomes the roof of the new workings. So that means that you need to leave a crown pillar. The thickness of that pillar depends on the strength of the rock and how much stress it can take. In some cases, the pit floor is reinforced with stress relief, drilling, controlled blasting, or by leaving a layer of ore untouched. Sometimes even the pit design is adjusted, like flattening the slope angles in order to straighten the collar pillar and protect the underground mine. So when the open pit is still active and underground construction has started, coordination becomes critical. You need to clearly separate work zones. Blasting the pit should never put underground crews or development at risk. A common approach is to begin underground work in areas where surface mining is already finished. For example, a decline is often started from the pit wall, about 50 to 100 meters above the bottom, and driven towards the ore body. This helps avoid lining up underground development with active blasting zones above. When underground mining happens beneath the crown pillar, strict rules also should be applied. While the pit is still in use, no underground voids are allowed directly under the pit slopes. If the chosen methods like block caving requires collapse up to the pit floor, that's only done after the surface mining is completely shut down and all people and equipment are safely out. This was actually exactly the case at Palabora mine. After pit operation ended, block caving causes the pit floor to collapse in 2004. And what happened is the pit deepened by nearly 400 meters and the major wall failure followed. That case proved one thing clearly. Never underestimate how fast and how strongly open pit and underground systems can affect each other. The construction of underground facilities must account for ongoing surface operations on the pit. This imposes special requirements for ventilation and dewatering. Unlike the open pit, which is naturally ventilated, underground workings need forced ventilation from the start. Even in early stages like shaft or decline development, you'll need fans and fresh air circuits and dust control systems. And one big challenge is to keep actually surface dust out of underground air intakes. Blasting on the surface can stir up a lot of dust, especially it's dangerous if it's pulled into the underground system. To manage this, mines often install separate ventilation shafts or exhaust raises outside the pit. Also, they can put temporary barriers or filters. For example, at the Grasberg mine, managing dust was especially tough. During monsoon season, dust combined with rain created fallout levels of up to 80 millimeters per hour, putting serious pressure on underground systems. Water is another critical issue. In the pit, it's nuances, but in the underground, it can be deadly. Water that builds up at the pit bottom from rain, for example, or groundwater must be pumped out consistently. If it seeps through rock fractures, it can flood underground workings. And that's where mud rushes come in. It's a sudden flow of water-saturated rock or sludge. They are one of the biggest safety risks during the transition. To prevent this, people use integrated dewatering systems, and existing pit wells are kept running. New drainage holes are drilled upward from the underground, and the surface pumping continues until the underground is fully sealed off. Some mines plan dewatering years in advance. In Argyle, for example, barrier wells were drilled around the pit early on, and groundwater levels were lower long before the underground cave zones were developed. Grasberg is actually a great example of well-planned transition. By 2015, years before the open pit was set to close, Freeport had already started developing the DMLZ and GBC underground mines. Ventilation shafts and key infrastructure were under construction early on. And thanks to that head start, the block cave system beneath the pit were ready when the final blast happened in 2018. Underground production began right on schedule in 2019. And still, even with all this strong planning, there was about a year and a half dip in overall output. To manage that, Freeport built up ore stockpiles in advance and used them to keep production steady during the transition. Another good example is Damshara diamond mine in Botswana tied to Geomechanical pit. Botswana invested $1.2 billion in building underground declines and extraction chambers, but there was still a gap between the end of surface mining and the underground mine reaching full capacity. During that time, they kept their processing plants running by feeding them low-grade stockpiles and rehandled material. So all these cases show a clear pattern. To avoid a total production drop, companies either extend pit operations a little bit longer, even at loss, or rely on stockpiled ore to bridge the gap. That's often better than a shutdown or losing skilled workers. With solid phase plan, it's possible to avoid at least major production gaps altogether. For example, at Palabora, when Block 1 started in 2002, copper production didn't stop. The decline in open pit output was matched by the growth in the underground mine. Even unexpected events were covered. For example, in 2018, a conveyor fire shut down Palabora's underground haulage system for 10 months, but thanks to advanced stockpiling, operations kept going. So talking about economics, evaluating the economics of the transition isn't that simple. It has to be an integrated approach. You can't just look at the pit or the underground mine in isolation. In the financial model needs to reflect both phases together. The standard tool is year-by-year cash flow modeling. This includes cost for building underground infrastructure, different production rates over time, and varying cost of open pit versus underground mining. The end goal is, of course, maximizing the project NPV. So to do that, project schedule is optimized. Open pit might run at higher output for a while, then taper off as the underground mine ramps up. The idea is to keep metal production steady because any downtime cuts into NPV due to discounting. Modern tools like mixed integer programming models helps with that. They show which ore blocks should be mined from the surface and which ones should be saved for underground. These models often reveal counterintuitive results, though. For instance, even if a block looks profitable in the pit shell, it might make more sense to mine it underground. That way, you can avoid the high cost of extra waste removal. In one case study, a sequential approach, which is pit followed by underground, delivered an NPV of $7.51 billion, with an optimal transition depth of around 887 meters, better than going fully open pit to the same depth. Another study found that optimizing the transition point boosted NPV by 2.06% compared to a non-optimized plan. That may not sound like much, but in large mine, 2% can mean hundreds of millions of dollars. I also want to mention that the transition to underground mining changes how we think about cutoff grades, which is the minimum grade that is still considered economic to mine. In the open pit mining, cutoff grades are usually lower, and that's because the cost to mine a ton of ore is relatively low. But as the pit gets deeper, costs go up, especially due to increased stripping. To stay profitable, the cutoff grade often rises towards the end of the pit's life. However, if an underground phase is planned, some of the deeper low-grade ore can still be reserved for later. Instead of pushing the pit deeper and spending more on stripping, mining can stop earlier and shift underground. The same material can then be mined more selectively and efficiently. This makes it critical to define both the final pit shell and the underground cutoff grade together. Underground mining usually costs more per ton, but it doesn't require stripping. So its cutoff grade is higher, for example, 1.5 grams per ton gold underground versus 0.5 gram per ton in the pit. During the transition, different cutoff grades are often used. High-grade ore may go straight to the plant, while the lower-grade ore is stockpiled until the final decision is made. Selectivity strategies change too. Open pit operations can tolerate small losses and dilution, typically 3 or 5%, but underground methods, especially like block caving, brings much higher dilution, often 10 to 20% of waste mixing in. This affects revenue projections. If you don't factor in lower grades from dilution, you just risk overestimating underground income. For example, in block caving, fragments of barren rock from the hanging wall can mix with the ore as it caves in. Each block must be evaluated not just by cost, but also by expected metal recovery after dilution and mining method. Some ore, like remnants in old pits or low-grade dumps, may not be even worth mining at all and are written off. So let's talk about the financial side. Transition to underground mining is capital intensive. Big investments are needed upfront, often while the open pit is still operating, and that's why the pit is expanded to finance the underground development, but spending large amounts early on lowers NPV due to discounting. To reduce that impact, companies break their investments into the phases. For example, they might first build declines and ventilation shafts. A few years later, they'll invest in underground equipment and transport. Final constructions comes last. This stage approach helps recover more costs from outgoing pit profits. Companies also look for outside funding. Partners or investors might finance the underground phase separately to avoid weighing down the current operations. Private firms often delay the underground start until it's really needed, like when grades fall or stripping becomes too costly, and this avoids having to invest in both systems at once. Alongside long-term planning, several short-term tactics help improve the project's economics. Well, first of all, you can be flexible in ore management. Near the end of the pit life, companies may mine high-grade ore zones more quickly and stockpile them, and these high-value ores can be used to keep output steady as underground production ramps up. Second of all, you can optimize the plant. When the pit's output drops, the plant may process tailings, backfills, or low grade just to stay running. Later, if underground output exceeds plant capacity, an expansion might be needed. These scenarios are modeled in advance to decide if extra capacity makes financial sense. And finally, you can control the cost. During the transition, per ton operating costs tend to rise. That's because the pit is winding down and the underground isn't at full capacity yet. Finance teams try to manage this by trimming fixed costs, like consolidating contractors, retraining staff, or selling off pit equipment. In some cases, equipment from the pit is reused in early underground work, like using drills or excavators for shaft prep. So in the end, you can see that economic success during the transition depends on dozens of small, smart moves, not just on choosing the right moment to switch. So, and I think that's all for today. Thank you so much for joining, and I'll see you next time.